So welcome to LambdaCube workshop. Just a quick question. Did anyone do graphics programming before? Or OpenGL, shaders? No. Oh, no problem. So that's not a requirement, just was curious. So LambdaCube will be different if you have experience before with this. It's a language. It's a pure language for graphics programming. It's domain-specific language. It has its own compiler, and it also has different backends for different languages. And the typical use case or usage for the LambdaCube system is that you write your 3D engine in the language completely, not just shaders, but every graphics processing part, and you just compile it with the compiler, and you use a library which is you choose from the existing backends, and you attach that library to your application, and that library, that backend, will load the intermediate representation of the compiled graphics pipeline. So basically, you outsource the graphics handling stuff to the LambdaCube system. The benefit is the ability to describe the whole engine in a pure way. So, but we know that, or if you use OpenGL, you know that it has a stateful API. It just models the actual hardware. But if you know nothing about the hardware, that this is the diagram in the left is a simplified model of the GPU processor. It's a stream processor basically with the hardwired steps. The green parts are programmable and the blue ones are configurable. And the diagram shows how a triangle gets processed. In graphics, everything is built with triangles. Yep. You can try, but maybe the images won't be zoomed. Not sure. It doesn't work. Just let me. Okay. Now remove that. Is it better? A little bit. So maybe the rasterization is the interesting part here. So it's just the step when the triangle gets filled with pixels, and that's also included in the hardware, and it's very efficient. So it's hardware accelerated basically. So anyway, OpenGL provides a stateful API to configure the graphics hardware. It has two types of commands. One is just for the configuration. You enable a feature, you upload, turn on a feature, turn off, or activate the program, so on. And then another one is called draw call. That's the one when actual drawing gets, so when it initiated, so when something will change in the screen. So the idea to model a pure description of the graphics pipeline is if we capture the setting of the hardware when the time when the drawing command is executed, then we can pass it as a argument. I mean, the relevant parts of the state are just the description of the configuration for that specific step. And LambdaCube does that exactly. So it introduces an EDSL operation for each hardware stream transformer, and where necessary, it provides the required configuration as a parameter. It's called this rasterization and accumulation context. So that's just the idea how it's possible to turn a stateful API into a pure one. If it is not clear, just ask. Maybe Do you have any questions so far? Okay. So it's a few words about the language. It has Haskell syntax plus some extra stuff like something what was relevant to graphics programming, that like vector swizzling. If you don't know that, what's that? That it's just a recombination of vector where you can create a new, like from a 4-dimensional vector, you can create another 4-dimensional vector by choosing the different parts of the components, or you can create a different shaped vector from like a 2-dimensional one. And the system also has a language also has a single tuple notation. It was a design decision in the compiler anyway, but just it's annotated with this double parenthesis. It's statically typed, it has type inference, and the interesting thing is that the graphics, so the hardware has a specific constraints, like not every operation is compatibility with other, and in this system it's enforced with type constraints. So it won't type check if it's not correct, or if it contains that constraint description. Okay, the most common operations what we will use is the linear algebra stuff like matrix vector multiplication or matrix, and the third one is a weird one. It's when we just scale a vector. The Prelude also has some convenient functions to create some specific matrices for perspective projections or just the lookup matrix or rotation. The last one is the function what we will use to sample a pixel from a texture. So it consumes a texture, and we provide the 2D coordinate on the image, and it just takes out that pixel. Anyway. Another operations what's built in the system, these are the stream transformers in the middle are the ones what models the hardware baked in things. The first two is the first one just creates an empty image. The second one we can combine two images like together, and the pipeline input is that's the syntax what we use to introduce the input variable to the system. We will see later how we use that. So let's see a simple example like this rotating square. You might see that if you run the preparation material. So this program consists of two files. The hello LC contains the pipeline description, and the hello HS is the Haskell application for that. The hello HS will load the pipeline, and we'll use the LambdaCube GL library to allocate the pipeline and execute it. This is just a help to see the correspondence between the hardware and the functional model of the pipeline. Like the first one, the fetch is the operation where we get so object is it's an array of 3D objects, and we specify here with these attributes that every 3D object what's in the objects array should have a position and the UV coordinate. And the map primitives is the primitive where we can provide the shader, vertex shader function. It's literally a function, pure function, but gets these two attributes what we fetched from the object array, and we transform it. And so this is exactly the pipeline what's used for this hello LC. So it contains the rotation matrix transformation. Then the rasterize primitives has two parameters. The one is the triangle context is the argument for the rasterizer, and the the second one, that smooth thing, it's a single tuple, what tells what interpolation should be used to fill the internal pixels of the triangle. So if you see before the rasterization, we have a vector, 3 vertices, and after it we have a filled triangle. And inside the triangle, the values, we can tell how they should be filled. And we might say that this should be interpolated, then we use this smooth thing. Otherwise, we can just say that let's use just the first one as a constant for each pixel. So anyway, the next step is the map fragments. That's the one what contains the fragment shader. It's a texture mapping function, so it has that texture to the call, and it also contains the sampler description. And the last one is the accumulate with this correspond to the pixels processing. That part is so the result will be stored in frame buffers, and the system has an initial frame buffer as well. I mean, when we render something onto an existing image. And with the pixel processing step, the accumulating with function, we can say how to combine the 2 pixels together. In this case, we say we won't use blending. There is no blending. We will just overwrite whatever is on this frame buffer. But we can turn on blending if you want. This is the actual code. Yep.
I just apologize. Is it possible to go back?
Yep.
Is UV a common thing in graphics programming?
Yes. It's just the name of the axis. Yeah. It's a U and V coordinate basically. It says that it's a 2-dimensional vector, and which the first one is the U and the second is the V.
So it's just like
just a
like X and Y or X and
yeah. Exactly.
Geometry to pixels on the texture.
Okay.
Actually, like if you unwrap the globe.
So this is the actual code what describes that pipeline what we've seen. It's formatted to look like a function, more like a function. So the main has this render frame which turns the pipeline into a frame buffer, and the make frame is the function what takes these 3 arguments, the time and the texture and the primitive stream. And as we see in the main part, we specify the inputs with names, like the time, and this is how we will refer for these inputs in the Haskell side. Okay. So let's see how things are connected. We have a description in LambdaCube which has a specific input type with the specific names. And the Haskell side, we have something called storage. Sorry for the diagram. It was an emergency to create it. Anyway, so we have this storage which should have exactly the same type and names like we used in the LambdaCube side. And the storage is so if the pipeline is the pure rendering function, storage is the argument for the rendering function. The third column is the GPU memory that the LambdaCube GL and provides a monadic API to upload resources like textures and geometry to the GPU memory. And the storage only contains references to that things. That means we can control when allocation is done. So it's predictive. Okay, this is the Haskell source code for the Hello HS. It's pretty simple. It uses LambdaCube GL and the mesh utility module, GLFW for window handling, juicy pixels for loading images, and the main function is just opens a window. That's the input schema is the is the type of the storage. That's how we describe it. But because so it cannot be a type. It should be a value because we load our pipeline runtime, so it's not in compile time. So this is just a simple EDSL to describe the shape, the type of the storage. It has this object which should contain triangles, and each triangle vertex should have a position and a UV coordinate with a two-dimensional float vector. And also the storage will store the time and default texture. So the next step, we allocate the storage with this alloc storage operation. Then we start to upload the data. Actually, for the quad we will have two triangles, and it's deliberately separated into two meshes, and which are defined in the end of the file. So these are the LambdaCube GL mesh data structure. It's just a map between the name and the vector array, basically. It's really simple, and it also tells it's a triangle. So we upload that triangle A to GPU, and the result the reference that will be a reference, we put it to the object slot of the storage. And also do the same for the triangle B. So with the true triangles, we will have a quad. And this next step, we load the image, and we also, with upload texture 2D to GPU, we upload it to the GPU as it says. And at that point, we haven't touched our pipeline at all. We just deal with the storage and the data. The next step, this example describes that alternative when we precompiled our pipeline. So it's stored in JSON. So we just load it and we allocate it. And the stat storage is the function where we connect the data with our pipeline. And it might fail because maybe it won't type check. I mean, maybe the shape of the input schema will be different. So that's why the result is a maybe. So anyway, if it is fine, then the only remaining thing is the main loop, where we just set the window size and provide it to the system, to the backend each frame, and we also update the uniform values every frame, like the time. And we call render frame for rendering, then swap buffer, the usual things, and that's it. That's the hello world for the system, basically. So now I quit here, and I just want executed. CD. Show. Stack. And here we go. So to continue, let's do something interesting, because this was a good start, but not very useful in the real world. So we've seen how to create a mesh. We can do it through vectors, but obviously the usual way we will load it from files. Like I chose OBJ format because it's very common. So it's every 3D software supports it. It looks like this one. It's a text-based format. Has the vertex descriptions and the reference to the materials and texture coordinates, normals, and the triangles using indices. The material description is also textual. The interesting part here is this line where we set the diffuse texture reference to this logo thing, to this file. Anyway, so let's check how this looks like. I built this convenience module for that to deal with this LambdaCube OBJ. it's built on, so it only uses what we've seen before, the LambdaCube GL and mesh. I used a library called Wavefront from Hackage, which supports OPJ loading. So what we do actually is just a conversion from this Wavefront OBJ to our mesh format. There are few functions what are useful here. The first one is load OBJ to GPU. It takes a file name and does everything. Load the OBJ and uploads this thing into the GPU. Then this upload MTL lib is so OBJ is the geometry, MTL is the texture, and the load OBJ to GPU gives us the texture name, but it doesn't load it. So we have to use the upload MTL lib for to do that. And we also need the function to put our model to the storage. That's the add OBJ to object array, the third one, this one. So let's check how can this be used. And so this time we won't load the pipeline description from file, but we will use the compiler as a library. Like we import it in the line 5. So the cool thing with this is we can recompile our pipeline during runtime. Basically, the rest of the program is kind of the same. So we define a schema and do the allocation, and here we load the object and the material and the object array. So the rest is exactly the same. So with this, we see this. Okay, so this time we reached the point where we can use actual objects. What we don't create, we downloaded something cool thing, and we might actually build something more interesting. And just a quick question: is this storage thing is it clear, or it's kind of important?
One question about the storage is: can it hold things other than objects?
Pardon?
Can it hold things other than objects?
Yes, it holds the uniforms and also the objects. That's the only two things what the pipeline can consume.
And how did you get the animation?
Oh yes, that's a good question. So pipeline is stateless. To get the animation, we have to we have to update the time each frame. And if we,
it's a pure function then.
It is. So this main is a pure function. This is the pipeline. It has the time, and if we don't update the time, nothing will happen actually. Okay. Yep.
Just being completely new to anything
no problem. Yeah.
Programming.
Sure.
I apologize. But with the time there, I'm wondering what's the mechanism that allows the rotation to occur.
Yes. Yep. So you see, we get the time from the Haskell side in here, and we pass it as an argument to this function, and it's actually consumed in the map primitives. In this, we create a rotation matrix where the angle is the time, and oh yeah, and also we multiply with a difference, so we rotate in two axes basically.
And is that an example of the swizzling that you mentioned?
Yep. You mean this?
Oh yeah, that one.
Yes, it is. So the thing is, we can even combine this with overlay. So it's because it's pure function is just we compose functions. Like I would say let's this time rotate it twice as fast, and we should see I don't know, maybe 2 cubes.
So the time, since it's pure, where does that time value change? How is that working on the Haskell side?
Yes, it is the Haskell side. Storage, so the graphics pipeline is a pure function, it's stateless. It has an argument, and we define the argument using this uniform. This is our argument type, basically. It's like row polymorphism or something. So if we introduce, it's not a record type, but it's an open thing, right? But when you compile this pipeline with the compiler, it collects everything and it closes it. So it will be a closed set. We will know what uniforms and what object slots does it have. And when in the Haskell side, when we load the pipeline or compile it here, this pipeline description has this information, what's the input for the pipeline. And we also, so we build our storage to store the values, like the time and the textures, but they are independent. They get connected only when we connect them here.
So it's not like constantly polling for the time and like changing the angle based on that. It's just an input parameter regardless?
Yes.
Okay, that makes sense.
And then the swizzle that you described is where the time with the rotation is updating a particular vertex of the vector, and then that's getting.
Oh yeah. So the processing mechanism is in the hardware. It's hardwired. It's I just programmed these parts, these stages, that you see there. So okay, it's fixed. But yeah, you're right. So
that's what is
exactly.
Okay. And I apologize too. The swizzling syntax. Could you explain just real quickly what does the percent mean?
The percent should be a dot basically, but it's we use the dot for function composition, and we just I'm pretty sure we will change in the future, but for now it was not a high priority to improve our parser and type checker to distinguish based on types whether this is a function composition or a swizzling operator. So this we just for simplicity we use the weird syntax for that.
So like if you wanted to like rearrange X, Y, Z, you would like from a vector, you'd like do the vector variable, then percentage sign, and then like say ZYX.
Yeah, you can. So the order doesn't matter. You can compound. It can be XXXX, YX, Z, or whatever.
Yeah, and it's basically accessors that then reorder.
Yeah. Mm-hmm. It's just a convenient way for that. Oh, cool. So we can deal with objects. Finally, let's build asteroids.
And one other thing like that's significant that comes to mind is that the storage is separate from the operations that are like the transformations.
Yes.
And that's very important because of the GPU having memory, I guess, because like you have to load the assets into memory.
Yeah.
You can't like flush them every time.
Yep, it's very expensive to move data.
So then the hot swapping, where you
Yeah.
changed what's in storage while the GPU is running the animation, and then you can, is that correct, where you could update what you're putting in storage without stopping the program?
Exactly.
And then the GPU will read whatever is in storage and apply the transformation of pipeline to whatever is in storage.
So what you can change is, so if you shut down the Haskell program, the storage will be lost. But because the pipeline is just data, it's a description, and it's explicitly connected to the storage, we can reconnect it later. Detach, attach, it doesn't matter. And the data won't be lost. What we uploaded to the GPU is stored by the storage. And it's not the pipeline. Okay. So for asteroids, let's start with a simple framework. I mean, just a skeleton with what has a main loop and opens window, has a simple pipeline with a white screen. I added some convenient thing here. So regular storage handling, and we have this load renderer function which tries to load and compile the pipeline, and if it succeeds, then it tries to allocate it, and if it succeeds, then tries to set the storage for that pipeline, and if it succeeds, it returns the new renderer. We will use it for hot code swapping. Also have this float time thing, this simple thing, and the main loop. Actually, I'm gonna use word wrap here. Okay. So the main loop is just the same thing, updating time and the window size and do the rendering, checking if, oh, here's the magic. We check if the pipeline modification time changes. If it changed, then we reload the pipeline. And so that means if I start this program, asteroid stack exec, it's white if I modify the, like, it should be changed.
So cool.
Oh, cool. So that's something, but not that particularly interesting. Let's for game data we have. Let me show. We have a spaceship, we have a missile, and an asteroid, and yeah.
Did you generate these object files with Blender? Is that?
I exported with Blender, but I used a freely available thing. So from where is anyway from TurboSquid. So let's just show an asteroid, load one and put it on screen. So I will cheat. I will use my patches to make it a little bit quicker. But you have access. If you checked out the repository, you can see all of that thing. Okay, just before I do it, I explain what's going on. So we import our convenience function to deal with OBJs. Then this load OBJ is just the wrapper which deals with errors. Then we load the asteroid and the corresponding material description. We use our upload function to upload the textures to the GPU, and then we put the object to the storage. That's what we're gonna do. Okay. Where was it? After storage. Okay. I think that is the Haskell part. The rest is we will have to write a new pipeline, obviously, because a blank screen won't do. But first I cobol stack build. So I run it first because we're done with the Haskell part.
Quick question as a project.
Yeah.
Some engines would make a big deal, rendering engines would make a big deal of the fact that they could instance items in memory. Do you get the same performance optimization of instancing a single object in memory multiple times? because it's a pure function operating from memory from storage, or do you need to make multiple items in storage to have multiple items on the screen?
So that's we need a specific draw call for that. It's not something to do with being pure or not. But at that moment, it's not supported. But there's nothing prevents to add that operation. So basically, what we need a new type of fetch. What will make instances
from the storage.
Yeah.
Right? Okay.
So this system is not ready for. Can be developed further, but it's a proof of concept thing, and it actually can be used to build something working stuff. And actually, I do it as a hobby because it's really cool to formulate everything to do graphics using purely functional concepts. Because in Haskell, even though Haskell is pure, but everyone is doing graphics uses OpenGL with the stateful API with the handwritten shaders, and that's not functional at all. Anyway, but they have the full control over the system. But if I do just to have fun, I think that's okay. We don't need this. Okay, so this one, we basically brought back our OBJ, what we've seen with the OBJ rendering. We have time, diffuse color is new, it's come from the OBJ's material description, and we have texture and the object, which has position, normal, and texture coordinates. At this time, for the Vertex shader, I refactored it to an explicit function, which that's one that calculates the result vertex positions using this camera transformation. So it transforms the vertices through this function. It applies a look-at transform, so it just moves the camera to a specific position and direction, and also applies the perspective projection. But these are the common operations what we would do anyway. I think if I saved it, it should already load up, but maybe I haven't saved it. No? Or it can have error as well. Yes. 25.
You accidentally deleted a line in the ls as you were around 25. Could you undo a little bit?
Where? I can check here. Yeah. So this is right.
Around 25 or so.
Here?
I think so.
Yeah, but this doesn't belong there. Okay, let's check the error message. Expected equality.
So it's probably above. Expressions not closed correctly. Is it because of the
Or
is LC in the white space sensitive?
yeah, it's just like Haskell. Did I? Yes, that's correct. Here you go. Thank you. Okay, not that interesting. So just a meteor or asteroid. For the next step.
Let me ask you a quick question. When you loaded the textures, I believe you said that the textures are loaded to the GPU, but are separate from storage, if I understood that correctly.
Yes, to check the code, I can explain it more detailed. Well, we won't see it here, but because it's already done in this function. But to answer your question is we have to go back to, I think, to hello. So see, this is the, with juicy pixels we load the picture, the image. Then we explicitly upload to the GPU. That's what I meant to it's separated. And it's not the storage. This is just uploaded. It's not, the storage doesn't contain it. Will contain until this line.
So say you don't fetch it from storage. You're using the image. It's associated with the OBJ by the MTL file.
Yeah, in the case of when we're doing with OBJs, yes, the MTL connects the images with the OBJs. But I thought that your question is regarding the resource handling or something.
Yeah, I just am curious about the modeling there. That would be in memory on the GPU, but it is not something that we are dealing with in the Haskell side.
No. It's just data uploaded, and we won't touch it anymore.
Can you upload a bitmap that you can change?
Actually, you can, but it's not. So OpenGL has an API to modify a buffer, but between frames, you won't modify a buffer while you're rendering a frame and using that thing. Okay. So when we're doing the rendering, it's constant because it won't be changed at time.
This is a static resource, and that's probably why it was designed. The storage wasn't designed to fetch images and apply them in the pipeline separately.
Okay. Any other thing? What wasn't clear? Still. All right. Let's continue. So we have this asteroid uploaded and shown. The next is. Okay. I haven't mentioned that, but I implemented the game logic in a simple way. It's so I have this object, the spaceship, with the position and velocity. For collision, we will use circles. So basic, deliberately basic solution. Asteroid is just has also position, velocity, and radius. This is the logical word, the game logic. And the missiles or bullets have lifetime, so they will disappear after a while. And we will also have particle system later on. And the top level data structure is word, which contains everything. The spaceship is maybe spaceship because if we destroy it, there won't be available anymore. Okay, and I use a explicit data structure for user input to deal with key handling, the keys. And also has a initial word setup with one spaceship and 2 asteroids. The only function what we will use and what's interesting here, so there's collision detection, stuff like that, but what actually is interesting is the step word. So we pass the delta time and the user input and the current word state, and it just creates the next one. That's what we'll use. Okay, so for the next step, let's add the spaceship to our game.
That's true. On the user input there for your step world, does that mean that there's only ever one allowable user input per delta of time?
Are you interested in the step word thing here?
Yeah.
Yes. Yeah.
So per unit of time, you can only accept one user input. It's not possible that a user could fire and rotate at the same time, for example.
It is possible, because the user input is the sum of the possible inputs.
Oh, gotcha. Nice. Thank you. That's awesome.
Okay.
Is delta time always like 1 second, 1 millisecond time?
Well, it's varying, but you're right. So to be more correct, it should be the same. But I did it in a way. Actually, we'll see in the patch. is here I calculate the delta in this line.
How do you keep prisoner state between frames?
It's pretty. It's a simple solution. I pass it as an argument.
Oh, so it's like in the closure.
Yes. Okay, so I started to add the things. I use data vect for linear algebra operations. Okay. Also, have to import the logic. And this is something new. We have to extend our input schema. Our objects will have positions and angles like the spaceship because we have to move it. So we extend add the new. Oh, not that line, like that.
You have like just one value for your angle, not like a 2
So the game will be just 2D with 3D models. So the graphics will be 3D, but you can move only 2D. Okay, the next is we'll just load the spaceship model. Exactly the same what we did with asteroid, the asteroid, and we have to upload the textures also from the asteroid and the spaceship. So instead of using this line, I just combine. They are monoids, and because they are, I guess it's maps or. Right, where am I? This comes here. Delete. Save. Okay, next thing, I up the spaceship object to the storage. And something new coming here. So this with this function, we add the spaceship mesh, this one, to object, and this list is we can list a set of list of uniforms what we require to be custom by this object. So that means there is a way to set unique value for each object, like unique positions. It's mandatory. Otherwise, we couldn't put them in different positions. The system works the way that there is a global set of value for every uniform. If we don't specify, if we just leave this empty, all the values would be used the global ones. If we specify if we require to have a per object a uniform, then we will have a custom value for the object. Okay. And the other convenient function. Okay, this enable object is so we can add objects to storage, but the enable object lets us to disable or re-enable them. That's really cheap. It's also possible to remove stuff from the storage, but that's more expensive. And maybe the amount of objects varies from frame to frame. Like if you do culling or something, we have to disable stuff. And so this disable object is just a convenient function to disable a full OBJ. And the add to scene will be used to add actually a position, set the OBJ position values. So we provide the position, angle, color, whatever we want to update, and it goes through I haven't mentioned it, but it's important to explain this. OBJ has the full model can have multiple materials, and each one object, if they have multiple materials, then they will be multiple objects. That's why it's a list. So one OBJ model is a list of LambdaCube objects. Possibly just one if they have only one material. But anyway, that's the explanation why do we have a list here. So we enable that object to be visible and also update the necessary input values. Okay. Yeah, it's we will see later on when we will do instancing how it works.
The spaceship, you were describing that the uniform value for position and angle is not the global. But where does that get defined, or where would you find that value? The spaceship's position and angle initially? Is it in storage?
The shape of data should be the same, so we cannot say here something what's not specified in the input schema. That's.
I'm sorry. When we on line 50 load the spaceship into the object array, the position angle attributes defined in that list.
Yeah.
Where do the position and angle values come from?
Well, at this, so when we put the spaceship to the object array, only the place is allocated for the values, and they are not initialized until we will call this thing. So this is something, this update object uniforms. It's not the same what we've seen before. It is just update uniforms.
Thank you.
Well, okay, a good question. Okay, let's see what's next. Okay, well, let's do the word. So we have to pass the word to the main loop every iteration, and the initial iteration will be the word 0 comes from the logic module, and the simulation. So we read the user input using the glfw input handling, create the user input value, and now calculate the data time and pass it to the step game thing. Okay, I think we created the new word here. I mean, for the next iteration, but what we should pass to the next as an argument. What I missed, as I remember, so this part is where we add the spaceship to the scene. It is after time. So as I said, spaceship is maybe type. So if it's nothing, we disable the object to hide it. If it has a value, then we call add to scene with the right values, what comes from this spaceship attributes. I think that's it for the Haskell side. So I'm gonna compile it. And we should see the same thing, but let's add the rest. So we will have two new inputs, the angle and position. It after the diffuse color. Oh, I saved it anyway. We'll get an error. Yeah. Where am I? So we have these two extra arguments. What we pass to the make frame of the color. This should be type correct. Yes. And finally, we have to use those values. I think, okay, the difference here is that we will have a new parameter, this position, and the angle in the end. And what we will use, we will use those that we will offset the position, the vertex position, by this position, what we got from the object thing, and also we'll use the angle to create a rotation matrix and multiply the vertices by that.